Beijing was sinking, literally sinking, a few centimeters every year as the city drank its own ground dry. And Beijing was not alone. Across northern China, entire cities were running out of water, and no rainfall, no river, no reservoir could save them. Because China's water problem was never about how much water it has. It was about where that water is. So China attempted something no country had ever tried at this scale: physically moving a river's worth of water across an entire continent. But between the water and the cities that needed it stood three problems. The first one was a law of nature itself, and engineers had to find a way around physics. The second one was an obstacle so large that going over it was impossible, and going through it was suicide. And the third problem? It doesn't end. It runs every hour of every day, forever. And if it ever fails, everything fails with it. This is one of the largest civil engineering projects in human history. And this is how China moved the water. First, understand the scale of the imbalance. 80% of China's fresh water sits in the south, in the Yangtze Basin and the rivers that feed it. 40% of China's population and most of its farmland sit in the north, where rainfall is scarce and rivers run thin. During the 1990s, the Yellow River itself ran completely dry before reaching the sea in some years. Cities kept pumping groundwater faster than rain could replace it, and the ground beneath them kept giving way. The answer was a system so large it defies comparison: canals, tunnels, and pumping stations moving billions of cubic meters of water every year across more than 1,000 kilometers. But the moment engineers drew the route on a map, they collided with the first problem. And it was not an engineering problem. It was physics itself. Problem number one: water flows downhill. Northern China sits higher. Water obeys one rule above all others. It flows from high ground to low ground. It cannot flow uphill. No machine, no budget, no political will can change that. And the route from the Yangtze Basin northward does not slope helpfully toward its destination. In key sections, the terrain rises. The water had no natural reason to go where China needed it to go. This was the law of nature standing in the way. Engineers could not break it, so they found two different ways around it. The eastern route follows the path of China's ancient Grand Canal. Along this corridor, the terrain rises steadily northward, and water has no natural momentum. Engineers built dozens of pumping stations along the route, massive facilities that lift the water over each elevation barrier, step by step, until it reaches the north. The central route did something far more elegant. Its source, the Danjiangkou Reservoir on the Han River, sits at a higher elevation than Beijing, meaning water could flow more than 1,200 kilometers by gravity alone. No pumping, no energy cost. But achieving that required a canal with a gradient so precise that water would keep moving across the entire distance without ever stopping. The central route drops just 100 meters across its full length, roughly 1 centimeter of drop for every 140 meters of canal. Any section even slightly out of level, and the water stops flowing entirely. Engineers surveyed every meter of the route using satellite data and precision ground measurements before a single section was dug, ensuring that continuous downward slope held across the full distance. Physics said no. Engineers said, not over the mountains then, around them, with them. Problem one, solved. But as the route pushed north, it ran directly into the second problem: the obstacle that could not be crossed. Problem number two, the obstacle that sits above the route. The central route runs north, and directly across its path flows the Yellow River, running east, cutting the route in half. But here is what makes this crossing unlike any other. The Yellow River is a perched river. Over thousands of years, it has deposited so much silt on its own bed that it now flows above the surrounding plain, held in by levees on both sides. At the crossing point, the surface of the Yellow River sits several meters above the transfer canal itself. Going over it was impossible. No aqueduct could carry this volume of water at this width. Merging the two systems was equally impossible. The Yellow River's heavy silt would contaminate the drinking water permanently. That left only one direction: down, under the river. And this is where the crossing earned the word suicide, because going under the Yellow River meant digging through fine sand and waterlogged ground, where groundwater pressure threatened to flood the excavation and bury everything in it at every single stage. Engineers began by constructing a massive cylinder shaft on the riverbank, 16 meters across and 50 meters deep. The largest and deepest water diversion shaft ever built on Earth. That shaft became the entry point for the tunnel boring machines, each over 80 meters long and weighing 1,100 tons, cutting through rock and sediment without disturbing the river flowing above. The result is an inverted siphon, twin tunnels beneath the Yellow River's bed, each large enough to drive a train through, stretching more than 3 kilometers bank to bank. Canal water flows down into the tunnels, passes beneath the entire river, and rises back up on the north side. Hydraulic pressure alone, the weight of the descending water, pushes it through. No pumping required. The Yellow River flows east above. The transfer water flows north below. The two systems share the same space and never touch. Problem 2, solved. But the third problem was unlike the first two, because the first two could be solved once. This one can never be solved, only managed, forever. Problem number 3, the problem that never ends. A canal is not a pipe. Water moving through an open channel is exposed to sunlight, to air, to runoff from surrounding land, and to natural processes that can turn slow-moving water contaminated and unusable. Across more than 1,200 kilometers of canal, carrying water to the taps of Beijing and dozens of cities, water quality is not a construction problem. It is a battle that restarts every single day. And a single failure anywhere along the route compromises everything downstream. Engineers lined the entire central root canal with concrete to prevent contamination from seeping in. Monitoring stations at regular intervals test the water continuously. Contamination, temperature, flow rate, oxygen levels, feeding real-time data to central control facilities. Automated gates can isolate any contaminated section without interrupting flow through the rest of the system. A strict buffer zone runs the entire length of the route, restricting industrial activity and chemical agriculture near the water. Crossing structures at every road and rail intersection were engineered specifically to prevent surface runoff from entering the canal. Water quality is monitored every hour of every day. And it will be, for as long as the system exists. The system has maintained drinking water standards since it began delivering to Beijing in December 2014. The problem never ends. Neither does the watch. Problem 3, solved, and still being solved every hour right now. The central route became fully operational in December 2014. The eastern route in 2013. Together, they supply water to over 176 million people. Nearly 80% of Beijing's entire water supply now comes from this project. Beijing's water table, which fell for decades, has begun to recover. By 2025, the project had diverted over 70 billion cubic meters, more water than flows through the Yellow River in an entire year. More than 1,200 kilometers of gravity-fed canal. Dozens of pumping stations, twin tunnels beneath the Yellow River, a 50-meter shaft through waterlogged sand, a total cost exceeding $62 billion. The water was in the south. The people were in the north. Engineers moved the water. Next week, China built the world's largest radio telescope inside a natural valley in Guizhou, a dish 500 meters across, listening for signals from billions of light years away. Building it meant solving a problem no observatory had ever faced. Fast, subscribe, and we'll see you next week.